Now we're going to tackle a very interesting optimization problem. So we're given a length of wire that is 100 feet long. So this distance right over here is 100. And it could be 100 feet, 100 meters, but we'll just call it 100 feet long just to annoy those of you who like to use the metric system. I actually like the metric system as well. But we'll just call this 100 foot long wire. And we're told that we're going to make a cut someplace on this wire. So we're going to make a cut someplace on the wire. And we're going to cut it into two wires. And on the left cut, we're going to turn this into an equilateral triangle. So this left cut right over here, the left section of wire, we are going to turn into an equilateral triangle. And the right cut of wire, we are going to turn into a square. We are going to turn into a square. And the question we are being asked is, where do we make the cut? Where do we make the cut in order to minimize the combined area of the triangle, the equilateral triangle, and the square? So where do we make the cut to minimize the combined area? So this is fascinating. So let's try to do this. So let's say that x is the distance between the left-hand side and where we make the cut. So let's call this distance right over here x. Then what's this distance right over here going to be in? So I'll do that in that same green color. So the length of the green wire is going to be x. Then what's the length of the orange wire going to be? Well, it's going to be 100 minus x. 100 minus x. So if the length of this is x, what is the area? What is the area of this equilateral triangle going to be? Well, we know what the lengths of the sides of the equilateral triangle are going to be. It's going to be x over 3, x over 3, and x over 3. And so somehow we have to figure out what the area would be if we know the sides of an equilateral triangle. So for that, I'll do a little bit of an aside here, just to rederive the area of an equilateral triangle as a function of the length of its sides. So let me do it a little bit bigger, actually, so I can derive it a little bit better. So if an equilateral triangle has sides of length s, 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 and s, and we were to drop down an altitude, just like that, so this is perpendicular, then this length right over here that I'm going to do in pink, this length right over here is going to be s over 2. S over 2. And to figure out the area of a triangle, you need to multiply the base times the height times 1/2. So we just need to figure out what this height is, which I will draw in blue. And we could use a Pythagorean theorem to figure it out. So if we call that height h, we know that h squared plus s over 2 squared plus s over 2 squared plus s over 2 squared is going to be equal to the hypotenuse, is going to be equal to the hypotenuse squared, is going to be equal to s squared, is going to be equal to s squared. And so we just have to solve for h. We can subtract this business from both sides, and we get h squared is going to be equal to s squared minus this thing, which is s squared over 4, minus s squared over 4. Well, you could view this, if you have a whole of something minus a fourth of that something, this is going to be equal to 3/4 s squared. This is going to be equal to 3/4 s squared is equal to h squared, or your height is going to be equal to the square root of 3/4 s squared. So it's going to be the square root of 3 times s, all of that over 2. So what's the area of this thing going to be? Well, it's going to be the base times the height. So let me write this down. The area of this equilateral triangle is going to be equal to the base, s, times the height, which is equal to s times this thing, times the square root of 3 over 2s, which is equal to the square root of 3 over 2s squared. So there you have it. We got our area as a function of s, of the area of an equilateral triangle as a function of the length of one of its sides. So based on that, the area of this thing right over here, the area is going to be equal to square root of 3 over 2 times s squared. Well, what's the length of one of our sides? It's x over 3. So we're going to square x over 3. So this is going to be equal to square root of 3 times x squared over 3 squared, which is 9, times 2, which is 18. So that is our area of our triangle, let me write a sub t. So area of our triangle as a function of x. Fair enough. Now let's do the area of our square as a function of x. So this is a little bit more straightforward. Each of the sides are going to be 1/4 of this. So they're going to be 100 minus x over 4. And then this is going to be 100 minus x over 4. So the area is just going to be 100 minus x over 4 squared. So it's just going to be, so the area of my square as a function of x is going to be 100 minus x over 4 squared, which is equal to, well, let's see, it's going to be 100 squared, which is 10,000, minus 200x plus x squared, all of that over 16. So what's our combined area going to be? Well, our combined area is going to be, and this is what we want to minimize. Our combined area as a function of x is going to be this business. It's going to be square root of 3 over 18 x squared plus all of this business. So right over here, let's see, we could rewrite this as 1 plus 1 over 16 x squared, and then minus 200 over 16x. So minus 200 over 16x. Let's see, if you divide both 200 and 16 by 4, you have 50 over 4x. And so you can divide, that becomes 25 over 2. So minus 25 over 2x. And then we have 10,000 divided by 16. So plus 10,000 divided by 16. Well, that's the same thing as 2,500 over 4. That's the same thing as 2,500 over 4. And let's see, 4 goes into 2,500. 4 goes into 25 6 times. You get 24. You get 100 here, so it gets 625. So plus 625. So I could rewrite this if I want to combine the coefficients on the x squared term. This is going to be equal to, and we get quite a hairy expression right over here, square root of 3 over 18 plus 1 over 16 x squared minus 25 over 2x plus 625. And so this is the thing that we need to minimize. And I'll do that in the next video.